Welcome to the 10th video in the series called Video Standards, Signals, Formats, and Interfaces. Today you will learn more standard dynamic range and high dynamic range technologies, different HDR flavors, signal levels, and perceived light levels. We'll also discuss some related myths, difficult questions, and marketing messages, and we'll reveal the inconvenient truths. Here are a couple examples of misleading wording. Saying HDR instead of a proper name like HDR-PQ or HDR-10 gives a false impression that PQ might be the only HDR format. Or saying you need a UHD TV to see HDR pictures is false. What's worse, not all UHD TVs support HDR, and standards allow all HDR formats in normal 1020 by 1080 HD resolution. So let's dig in. Light levels ratios are traditionally specified in stops. One stop means doubling or halving the amount of light reaching a camera's sensor. The humanized dynamic range is very large, about 24 stops. However, the range of discernible light gradations, while viewed simultaneously, is much smaller than that, less than 12 stops. These facts lead to these inconvenient truths. In a well-lit living room, standard dynamic range and high dynamic range dark gradations look the same. SDR white on a modern screen is not 100 nits, it's much higher. And it's limited only by the particular display's design and electronics. HDR white is not higher than SDR. It is in fact lower than SDR white. Typical HDR images are dark. Only the specular highlights are much higher than the clipped highlights in SDR images. The subjective perception of color video images, light levels, may differ significantly from the photometric brightness as measured in candelas per square meter, abbreviated as CD over M squared. The common answer to the question, which color bar in this test pattern is brighter, is all bars except black are equally bright. This leads to the de facto formula of perceived light levels, measured in nits or percents, in which the weighted sum of the CIE formula is replaced by the max RGB function. So, the perceived light levels measured in nits coincide with CIE brightness values measured in candelas per square meter, but only for shades of gray. Today we have at least 4 different video formats based on different signal-to-light mapping schemes called dynamic range models. There's the traditional standard dynamic range model, or SDR, in which only relative brightness is important. There's the widely used log camera format, which is used only in production and post-production, and it deserves a separate explanation. There's the perceptual quantizer model, called PQ, which is the foundation for 3 major HDR formats: Dolby Vision, HDR10, and HDR10+. And there's the hybrid log gamma model, which is a sort of halfway house between SDR and HDR log. All displays convert signal levels to light levels in accordance with their specified electro-optical transfer function, or EOTF for short. Absolute mapping schemes work only for the HDR-PQ systems that use the target device max brightness concept, which was borrowed from digital cinematography. All other systems use a traditional model of relative light levels, so actual screen light levels depend on the display's own particular design, electronics, and user controls. Unlike SDR, HDR-LG, and HDR-log, the HDR-PQ electro-optical transfer function sets the conversion law of relative RG&B signal levels to absolute light levels. The maximum output of a typical HDR display is significantly lower than the PQ format limit of 10,000 nits. Therefore, the HDR-PQ content must be produced and/or converted for a variety of target device maximum brightness values. HDR-PQ reference white level and related diffuse white level are not yet defined, although the de facto value is thought to be 100 nits. Standardization is needed, but the introduction of any HDR-PQ reference white level measured in nits makes it practically impossible in any outdoor production, such as sports event coverage. A return to the traditional definitions of reference white as a scene-referred relative value contradicts the fundamental PQ idea of absolute light levels reproduction. For example, with the HDR display white set to a fixed 100 nits, the rendered human face light level must be 20 to 40 nits. In a sunny beach scene or dark cellar episode, the brightness of all faces on screen must stay about 30 nits, and that's nonsensical. HLG EOTF converts relative RGB signal levels to the relative light levels, and that's a traditional scene-referred approach. Unlike SDR, the maximum 100% relative light level of HLG format is 3.8 times higher than the reference white light level, which is set at 26.3%. The HLG format is 3.8 times higher than the reference white light level, which is set at 26.3%. The HLG format is promoted as being backwards compatible with SDR production and distribution, with no metadata required. But this is debatable. For example, HLG reference white on a compatible SDR screen comes out as 50% light gray, which is much lower than 100% white. What is wrong with this diagram illustrating the differences between HDR and SDR? Unfortunately, almost everything. BT709 SDR standard does not define nor require a 100 nits display. SDR display brightness is unlimited. The sky's the limit. BT2020 PQ format allows high light levels, but only for specular highlights, not for flat areas or occupying full screen. In SDR, full screen white is normal. So this is an unfair comparison of apples and oranges. Perceived colors of about 1 nit and below collapse to neutral gray. In other words, all cats are gray in the dark. Therefore, the lower portion of the diagram should shrink to one central point. This also applies to the colorless upper portion. 75 years ago, David McAdam measured color vision thresholds and plotted them on a non-uniform CIE XY plane as ellipses of quite different sizes. That's why on an XY diagram, the HDR triangle appears much larger. Mapped to the fair play uniform CIE 1976 coordinates, two chromaticity triangles are not very different. Colors change appearance depending upon their absolute luminance and upon their surroundings. This happens to be the biological foundation of most of the optical illusions you've ever seen before. The recently published SMPTE ST 2080-3 2017 standard defines a reference viewing environment for evaluation of HD TV images, which should not be confused with anybody's typical TV viewing conditions. The ITU-R BT500 standard defines very important international 5-grade quality and impairment scales and a 7-grade comparison scale, as well as the important anchoring methodology. It's a well-known fact that HDR images and color grading procedures which are suitable for a home theater are often not suitable for a living room. This leads to the question of where is the main target market for the HDR content? Is it A, the color grading room? That's not a joke. It could very well be the right answer. Or B, some dark home theater? Which ones? Or C, a well-lit living room? In afternoon sun or midnight chandeliers? Which target market is more important? Is it possible to deliver the same HDR content to all types of customers? Can embedded metadata even help at all? Keep watching this series. This video was prepared for you by a team of experts. Produced and narrated by Joseph Mark, a member of SMPTE's HDR committee. Written by Dr. Victor Steinberg, co-founder and president of VideoQ, Technical Awards winner, and author of the Video Standards book. Conceived by Roderick Snell, co-founder of Snell & Wilcox and winner of several technical Emmys and Queen's Awards. Technical consulting by Maxim Levkov, author of the Video Encoding textbook. This video series is brought to you by VideoQ, and you can download these slides and this video from VideoQ.com. VideoQ makes products and services for all sorts of video and audio processing and quality assurance. Based in Silicon Valley with software developers and distributors in several countries. Thank you for watching.